This is video for 8.1 absolute value functions. So we're just introducing the idea that we can put these absolute value lines around any function that we've previously seen, and it's going to impact what my graph ends up looking like. So let's have a look. So the first thing we need to do is acknowledge the fact that we've got y equals x is what we call, or what we're going to call, the parent function. Okay, and what that means is that that's where we're going to start. That is what our new function is going to be based on. Then we have our y equals the absolute value of x. Now, because we're taking the absolute value of a variable, that is what makes this an absolute value function. Okay, so when you go to graph an absolute value function, or any function really that we want to kind of manipulate, the key thing you want to understand is that we've got our parent function that we're going to then change. So we can start by actually figuring out our points on our parent function. So y equals x, so they're going to be the same value. So when x is -3, y is -3, and so forth. But when we take the absolute value of that output, or that original function, to get our new output, what happens is that all those negatives become positive, and that's the impact of the absolute value, turning negative into positive. So instead of -3 for y, we're going to have +3. 2, 1, 0, 1, 2, 3. So what does that look like graphically? Well, we've already got our scale here, so that's kind of nice of me that I gave you that. We've got x and y. Now my points in my original function I'm going to do in red. So I've got -3 and -3, -2, -2, -1, -1. Okay, so I've got all those points, and that makes a straight line. So if I wanted to, I could extend it beyond there. Sorry, it's a little bumpy. Okay, my next piece is that I'm doing the absolute value of this, and so some of these. So all my points that were positive before stay positive. These are what we call invariant points. So 1 and 1, 2 and 2, 3 and 3, and so forth, extending that way, starting at 0 and 0. So all of this is invariant. What that means is that it's not changing between the parent function and the absolute value function. But everything below 0 actually does change in terms of my y value. So 0 is special. It's what we call the critical point. If I could spell, that would be helpful. Okay, and what that means is that it's the point where our parent function and our new function diverge, or vary, or change. And so what happens over here is that x is -3, y is +3. We get points on this side, which means what actually happens is, instead of a straight line, we get a V. Now, the general shape of this graph doesn't change. We still have a straight line on this side. It's just that it's going in the opposite direction. It's being flipped above the x-axis. So just because it's symmetrical and going up on both sides doesn't mean it's a parabola. We actually get what we call a cusp. And what that's referring to is the fact that it forms this sharp point. Okay, so that's what taking the absolute value of a parent function does. So we've got kind of some of our keywords here. Absolute value function is when we take the absolute value of some parent function. So again, okay, oh, and I should probably label this as y equals the absolute value of x, whereas my red function is just y equals x. It's always good when we're putting more than one graph on the same grid that we recognize which one is which equation describes which line or function. Okay, the x-intercepts, this is in general, your critical points are going to be your x-intercepts of your parent function graph. So those are going to be your point of inflection, the point where it changes direction. All your invariant points are the ones that remain unchanged when transformed. Okay, so the invariant point of an absolute value function is the x-intercept. We also have a lot of other invariant points. All of those positive ones didn't change either. Okay, the last idea that we haven't looked at yet and we haven't heard about is what we call a piecewise function. Okay, now because of this weird cusp, this sharp point, we can identify that these are actually two separate pieces of the same graph. So this left-hand side and the right-hand side are actually could be expressed as two different functions because of that sharp point. If it was curved, we would say, okay, well, it would still be recognized as a single function, but when you get into calculus, you start learning about continuity a little bit more in depth than we did in grade 10, and you'll see that a cusp like that actually is a discontinuous point. So instead, what we're going to do is we're going to break down the function into two pieces. We first of all identify, so step one is identify your critical points. Step two, identify where your graph is invariant. Okay, this means that you can keep the original parent function to represent that part. Okay, and step three, we're going to identify where the absolute value of your parent function is different than f of x. And that is where we're going to reflect. Your parent function to define the equation. So what that looks like is, in this particular case, my invariant point, or my critical point specifically, is 0. And my invariant points, where it overlaps with my parent function, is when it's bigger than 0. So when I write my piecewise function, I'm going to write y equals, and then my normal parent function, y equals x, if x is bigger than or equal to 0. So that is for all the invariant. Okay, but I'm going to put a negative out in front of my whole parent function if x is less than 0, because I need to reflect it over the x-axis. So I need to kind of like take the negative of it, because otherwise I would have ended up with negative values. So I need to recognize that I need to change the sign from my parent function. And we see that here in our table of values from negative to positive. Well, if we take negative of -3, then that's equal to +3, which is what we did right here. Okay. So that's kind of what all those words mean. To kind of wrap our heads around it, to summarize, since the absolute value cannot be negative, the part of the graph of y equals x that is below the x-axis is reflected in the x-axis to become y equals negative x through this interval. While the part that remains unchanged stays the same in terms of the equation, and we state the interval for that as well. So when we look at this equation, first of all, what shape is it making? Well, I see 2x minus 3. So if we were to imagine this is y equals 2x minus 3, this is what we would call our parent function. This is a line. This is y equals mx plus b. Okay, remember m is our slope and b is our y-intercept. So part A asks you for the y-intercept and the x-intercept. So our y-intercept is already given. It's negative 3. But that's for my parent function. So I'm going to do everything for my parent function and then I'm going to manipulate it. My x-intercept, I'm going to need to plug in y equals 0 and solve for it. So 0 equals 2x minus 3, so 3 equals 2x, or x equals 3 halves. Okay, that is my critical point. But my y-intercept, and okay, parent and absolute value. So remembering that my y-intercept can't actually be negative, that I can't have negative y values if I've taken the absolute value of my function, my y-intercept is going to be reflected. So for the absolute value, it's going to be positive 3. Now my x-intercept, because it's my critical point, it is unchanging. It's part of my invariant points. So that's going to stay the same. So I'm going to sketch my graph now that I know this. So I've got my y values, and I've got x-axis here. This is my origin. We're going to go 1, negative 1, negative 1, and 1. Actually, I'm going to go by half since I've got lots of space. This is going to be 1, negative 1, negative 1, and positive 1. Okay, so if you do like drawing the parent function, go right ahead. Put your y-intercept and draw your slope. Go nuts. If you're going to do that, I'm going to get my y-intercept as negative 3. Go up to over 1 is my slope. And this is going to be my parent function. When I want to draw my absolute value, now we can visually see why my y-intercept changes. It's because anything below my x-axis becomes positive. My output needs to be positive if I'm taking the absolute value. So my critical point is 1.5 or 3 halves. And all the points from there are going to go in the opposite direction. Instead of being negative, they're going to be positive, and so they're going to go upward as well. This side stays the same. All those invariant points, they were already positive, they don't need to change. And so this is my y equals absolute value of 2x minus 3. Okay, so I've got it graphed. Excellent. So A is done, B is done. State the domain and range. Well, for my parent function, my domain is negative infinity to positive infinity, and my range is negative infinity to positive infinity. All values are possible. My line keeps extending downward forever and upward forever. And remember, when you write domain and range, always write your smaller value first. What happens when I take the absolute value is that I get a minimum all of a sudden, which means my y value, my vertical values, are restricted. I do not pass this point. I do not pass my x-axis. So all of a sudden my domain becomes restricted, or not my domain. My domain stays the same. I continue going left and right forever. I've got negative infinity to positive infinity, but my range is restricted. My y values stop here and then bounce back. I do not go below 0, but I go to positive infinity still. So remember, a square bracket when you have a defined point. So C is done, and minimums and maximums restrict your range. Finally, for part D, express as a piecewise function. So y equals open curly bracket. Now, I always like to list my invariant points first. It's just a personal preference. So I'm going to use my parent function, 2x minus 3, if, and that's going to be defined from 3 halves, my x-intercept, my critical point, and upward for all increasing x values. That's where it didn't change. So x is greater than or equal to 3 halves. But it is variant everywhere left of this. So I'm going to change all my signs. It's like putting a negative out in front of the whole thing. So it's going to be negative 2x plus 3 if x is less than 3 halves. Now you'll notice that only one of them is defined as equal to. If we define them both as being equal to 3 halves, then all of a sudden we've got 2 overlapping points, and that's not allowed. Okay, so we can actually do the same idea when we're dealing with quadratic equations or quadratic functions in addition to linear equations and linear functions. So the first thing you want to do is just work with the parent function, and then we'll see what happens when we take the absolute value of it. So when we take negative 4 and we plug it in here, we get 16 minus 8 is 8 minus another 3 is going to be 5. Then we get negative 3, so that's 9 minus 6 is 3, minus 3 is 0. Negative 2, plug it in and complete the table for this one. You guys know how to do that. So we fill in this chart, and to take the absolute value of anything means we're taking the positive version of it. So we're taking, in this case, everything in here. We solve that first, then we take the absolute value. Well, we've already solved that inside piece. It's right here in our parent function. So we're just going to take the absolute value. Well, the absolute value of a positive is a positive. So all of a sudden, I know that these points don't change. It's just these ones in the middle become 3, 4, and 3 instead of negative 3, negative 4, and negative 3. So when I go to graph this, it's going to look a little bit different. I'm going to have to zoom out a little bit here. So here we go. So pause the video right now. I'd like you to graph at least the regular quadratic equation on your own so that you get some more practice. Okay, so I've got my parent function here. I'm just going to label it as that, save myself some writing. Now I want to take the absolute value of it. Well, anything that was positive we said stays the same. Those are all our invariant points. All through here. critical points are intercepts always. And now everything below is reflected. And so we've got 3, 4, and 3 here. I'm going to sketch my parabola as if it was upside down. Oh my goodness. If it was upside down. There we go. Not beautiful. I'm not sure why I did that. Okay. So, this is my absolute value of my function in blue. You'll notice that again, everything that was below my x-axis is now reflected upward. So in this case, when I go to write my piecewise function, I would keep it the same as my parent function in 2 places. So I would say x squared plus 2x minus 3, and that would be defined for the following 2 places. Either x is less than or equal to -3, right here, or x is greater than or equal to +1. So those are my 2 cases where I have invariant points. Alternately, I'm going to have -x squared minus 2x plus 3 if x is between my 2 critical points. So -3 is going to bookend it at that end and +1 at the other end. Now again, notice I didn't put equal signs there because I don't want it overlapping with the points I've already defined. Shot, so let's give this one a shot. We've got -x squared plus 2x plus 8. Now, if you don't want to actually graph the whole parent function, I like to have a sketch of it just to kind of refer to. So if I want just y equals -x squared plus 2x plus 8, it's opening downward. My y-intercept is at +8. And I could even factor this out to figure out my x-intercepts. I would take the negative out. It's -8, -2, so it's going to be x minus 4 and x plus 2. Give me that. So now I've got my intercepts, +4, -2, which means my vertex is somewhere here. And it's not beautiful, but I have an idea of what my parent function is going to look like. And I've done some of the work for part A. So in this case, I'm not going to list my parent function values. I'm going to jump directly to my absolute value. So my y-intercept is +8. And my x-intercepts, I figured out by factoring. Again, the first thing I did was take out that negative in front of x squared. Then I can factor it like a regular trinomial. And I got +4 and -2. So part B is sketch the graph. Well, now that I already have a sketch of my parent function, just very roughly over here, it's going to make my life a little bit easier. So I know because it's an absolute value graph that I'm going to be mostly in the positive. Actually, I'm going to be exclusively in the positive. So I'm going to put my x-axis a little bit lower down. Okay, and because I have to go all the way up to 8, I do want some room above it. So that's another good reason to put my x-axis a little lower down. I'm still going to go up by 1 in this case because I am going quite high on my y-axis. And don't forget to put a y and x on there. So let's define some points. Y-intercept, 1, 2, 3, 4, 5, 8, right here. X-intercepts, -2 and +4. Again, I can figure out my vertex point a couple of different ways. The best way to do it is to go exactly halfway between your 2 x-intercepts, and then you can just solve for y. So I'm going to be working with x equals 1. If I plug that in, it's going to be -1 plus 2 is +1, so it's going to be at 9. And so I've got all of this is going to be invariant. All of this is going to be invariant as well. Now I know that because it's already positive in my parent function. But what happens at my critical point? Well, my critical points, my x-intercepts, reflect my graph. So it's going to be like my parabola was opening upward instead. And so I'm going to get this effect on the outsides. It looks pretty weird. You want to try and make them symmetrical. So, something along those lines. That's going to be my graph. So again, sketching the parent function is very, very handy in my opinion, but I'm a visual learner. If you're not visual, go nuts. You don't have to. Domain is going to be negative infinity to positive infinity because we still can go left and right forever. But our range is restricted by that absolute value. We're saying that we cannot go below 0. We can only go above it. Finally, state this as a piecewise function. So in our case, it was invariant in the middle. So when I go to write this, negative x squared plus 2x plus 8 is going to be if x is between, so I'm going to list negative 2 is less than or equal to x, is less than or equal to positive 4. So in the middle, that's where it didn't change. It does change, so I change all the signs, not just my first one, if on two occasions, x is lower than, not equal to, just lower than negative 2, okay, left of negative 2, or x is greater than positive 4. So those two scenarios come to mind. And that's how we do it. So example 3 and example 4, I'm going to fill out the answers and I'll kind of show them to you, but I'm going to leave them.
Office, please. Miss Mann to the office.
I'm going to leave them for you to try on your own, just so that you kind of get to experiment with how you like to do it. Do you like to draw the parent function? Do you like to make that table of values? Whatever you want to do, whatever strategy works for you, give them a shot, play around with it in these two examples. So looking at example 3, I've done all the work, so make sure that you actually know how to do this. Try it yourself, okay? My y-intercept in my parent function should be negative 2, but because I'm taking the absolute value, I had to switch it to positive 2. I had to factor my parent function in order to determine my x-intercepts. You could also use your quadratic equation, but I prefer factoring when possible since that quadratic equation is a bit of a monster. I sketched out my parent function up here just so I had an idea. Yes, it's opening up, so where are my invariant points and what's changing? That always helps me in terms of sketching my graph, but also in terms of writing my piecewise function. And so again, remember, when you're writing your piecewise function, it's negative, positive, positive, because we change the signs of every term in that parent function, not just the first one. And I also don't have less than or equal to signs here because they're already defined points up in the first part of my piecewise function. So again, pause the video, try example 4 on your own. So example 4 is a little bit trickier. So before I did any of this, I actually sketched out my parent function. I treated it like it was in vertex form, which meant that my vertex was at 0 and negative 1, and it's opening downward. So I've got my 0, negative 1, opening downward, which means that my entire parent function is all in the negative side of my graph. It also means that I have no x-intercepts. So this is going to make it interesting. It means that literally my entire graph is reflected upward. So you'll notice that my scale is a little bit different. On my x-axis, I'm going up by 1/2, but my y-axis I'm only going up by 1, and that's because I also have a huge stretch in the form of 3. So I want to kind of give the best picture I can for my graph, so I'm going to play with my axes. I could have even gone a little wider and gone up by like 0.25, but 0.5 is at least a little bit better, a little less narrow. So I found my vertex. I plugged in some other points to try and define where they were. This is going to be at 1 and 4 here. This is at 2 and 13, if I'm not mistaken. And then vice versa on the other side. Okay, so you plug in values to find those. What's crazy about this is that my domain then again becomes negative infinity to positive infinity, expanding forever outward. But my range now is defined by my vertex. I don't have any critical points, which means that my range is defined by my minimum, which is above 0. So I can say that my range is starting at 1. Okay, so that's a little bit different about this equation. Also, because I've flipped my entire equation, there's no cusps, there's no critical points. The entire thing is variant from my parent function. And so I'm going to just write a single equation, and we could define it as x is an element of the reals. That would be totally fine, but the reality is this is my new equation to define the absolute value of my parent function. So there are some scenarios where we do not have x-intercepts. Don't panic. It's not the end of the world. This is how we deal with it. So you've got lots of practice questions. Now you'll see this note at the bottom of the page. Disregard that. I'm going to combine R2A and R2B to be just R2. So you'll do that assessment after the last lesson for this unit.